Hi everyone. Welcome to ILTA Physics Online Lectures. Today we're going to learn about a super useful tool in dynamics for analyzing the forces acting on an object. It's called a free body diagram. A free body diagram that it works kind of like the Rosetta Stone did for ancient Egyptian hieroglyphs. It helps us decode what's going on with forces. Just as the Rosetta Stone unlocked the meaning of ancient writing, the free body diagram unlocks our understanding of the complex forces acting on moving objects. In this lesson, I'll briefly explain what a free body diagram is and walk you through the steps to draw one. Next, I will show you some common types of free body diagrams that you'll see often in physics problems. And finally, we'll compare free body diagrams to Newton's third law of motion, the action-reaction law, to wrap up today's class. Let's first review Newton's three laws of motion, which we covered last time. Last time, we learned about Newton's three laws of motion. The first law is also called the law of inertia. It says that unless an external force acts on it, an object will keep doing whatever it was doing. In other words, if something is at rest, it'll stay at rest. If it's moving, it'll keep moving at the same speed and in the same direction, unless something messes with it. So basically, Newton's first law tells us what happens to objects when there are no outside forces. Newton's second law is called the law of acceleration. If a force is applied to an object, that force causes the object to accelerate. And by acceleration, we mean any change in the object's velocity. That could be starting from rest, speeding up, slowing down, or changing direction. Newton wrote this in math form as the famous F equals ma. This means that acceleration is directly proportional to the force applied, and inversely proportional to the mass of the object. The direction of the acceleration is the same as the direction of the net force. Here, the force means the net force, the vector sum of all the forces acting on the object. Newton's second law is about how an object moves when there is an external force. This equation also shows the connection between kinetics, the study of forces, and kinematics, the study of motion, the two major branches of classical dynamics. On the left side, we have force, which belongs to kinetics, and on the right side, we have mass and acceleration, which belong to kinematics. Newton's second law is what links these two together. Pretty interesting, isn't it? We'll use this relationship to solve many dynamics problems in our next lesson. Finally, Newton's third law is the action-reaction law. It explains how forces work between two interacting bodies, called an agent and an object. If object A pushes on object B, then object B pushes back on A with a force that's equal in magnitude but opposite in direction. In math form, we show this with a minus sign to show the opposite direction. Here's an example. If you bump your head into a glass door, it feels like the door hits you back. That's exactly Newton's third law in action. All right, now let's take a closer look at how forces act on an object. First, always remember this. Whenever there's a force, there's always something applying the force, the agent, and something receiving the force, the object. A free body diagram FBD is a tool that helps us visualize and analyze all the forces acting on an object. The goal is to figure out the net force acting on the object. In a free body diagram, we draw the object as a single point, and then we draw vectors for all the forces acting on it from different sources. Look at the diagram on the right. There's one object, shown as a single dot, and two forces acting on it: gravity pulling down and the normal force pushing up. Since they're equal and opposite, the net force is zero. This is similar to the motion diagrams we looked at earlier. Those show displacement, velocity, and acceleration of a motion, while free body diagrams show forces. Let's draw a diagram now. Now let's walk through the steps to draw a free body diagram. Look at the bottom right figure. There's a bag sitting on a table. Let's treat the bag as our object and draw all the forces acting on it. Step 1 is to understand the problem and mentally identify all the forces acting on the object. Honestly, if you do this part well, you've already solved most of the problem, about 80%. It might seem a bit unfamiliar and hard at first, but after you go through a few problems, you'll start to see a very typical pattern. In this case, Earth pulls the bag down, that's gravity. And the table pushes the bag up, that's the normal force. You'll get better at recognizing these forces with practice. Step 2 is to choose a coordinate system. As we learned earlier, this means deciding the origin and the positive directions. Usually, we use the regular XY coordinate system and place the origin at the object's location. In this case, let's place the origin at the bag and use a standard vertical and horizontal axis. But if the object is on a sloped surface, then we often tilt the coordinate system to match the slope. We'll cover an example of that soon. Step 3 is to draw all the forces as arrows, representing vectors, starting from the object. Please pay close attention to this part. Every force vector must start at the object. That means the tail of the arrow is always on the dot that represents the object. That might feel a bit weird, but that's how free body diagrams work. In our example, we identified two agents of force, which are the Earth and the table. First, the gravitational force from Earth. Gravity always pulls down toward the center of the Earth, so we draw a downward arrow from the point. Label it as W, which means weight. Next, the normal force from the table. This is an upward force perpendicular to the surface, so we draw an upward arrow and label it as N. Now let's find the net force acting on an object. To do that, we add up the vectors. Since both forces are equal in size and opposite in direction, they cancel out. So the net force is 0. Alright, let's take this one step further. When the net force is 0, Newton's first law applies. If the object is at rest, it stays at rest. So we just explain the motion of this object using a simple free body diagram. Next, we'll take a look at different types of motion and draw their free body diagrams too. Let's start with a free body diagram for motion in the horizontal direction, specifically for the spring force. As you can see on the left, let's say an object is attached to the end of a spring that has a certain natural length in its normal, unstretched condition. This normal condition is also called the equilibrium state, which we'll discuss in more detail later. Now, imagine that someone pulls the spring to the right, stretching it. Let's draw the free body diagram for this situation. Here, the object is the small block attached to the end of the spring. In the first step, let's think about all the forces acting on this object. Since the spring is stretched and held still, there's a restoring force pulling it back toward the left. That's the spring trying to return to its original position. At the same time, there's an equal force from the hand pulling toward the right, balancing the restoring force. In the second step, we'll set up our coordinate system. We'll take the object's position as the origin and use a standard two-dimensional XY coordinate plane. Now for step 3, let's draw the two forces, the spring's restoring force and the hand's pulling force, in our free body diagram. The spring's restoring force, which pulls the object back toward the equilibrium position, is drawn as an arrow starting from the object and pointing to the left. We'll label that force as the spring force. The other force acting on the object is the person's hand pulling to the right. So we draw another arrow starting from the object and pointing to the right. We'll label that one F hand. Now finally, let's find the net force acting on this object. Since the leftward spring force and the rightward hand force are equal in magnitude, they cancel each other out. so the net force is zero. Physically, this means the spring stays stretched but not moving, and since no unbalanced external force is acting on it, it remains at rest. If you carefully follow these steps and draw your own free body diagram, you'll understand this concept very clearly. Now let's move on and look at a free body diagram for a slightly more complex type of motion. In the picture on the left, as we mentioned before, a small child is sitting in a toy car, and two of their friends are pushing the toy car to the right. Let's take the car, or the car with the child in it, as our object. Now let's go over a very classic and typical type of force problem here. Whenever an object is moving on a flat surface, there are three main forces that we always need to consider. The first one is gravity, which pulls the object downward toward the earth. It always acts vertically downward and is usually labeled as W. The second force is the normal force. When an object is resting on a surface, that surface always pushes the object upward, perpendicular to the surface. Normally, this is an upward force, but if the motion is on an inclined surface, the normal force acts perpendicular to that slope. That's why it's called the normal force, normal meaning perpendicular. The third force we have to think about is friction, the force between the surface and the object. Friction always acts in the direction opposite to the motion, or opposite to the direction the object tries to move. So again, let's summarize this. Whenever an object is moving on a surface, there are always three forces acting on it: gravity, normal force, and friction that acts opposite to the motion. That's the first step when drawing a free body diagram. All right, let's go back to our example of the toy car being pushed. Since there's nothing special about the coordinate system here, we'll just use a regular two-dimensional XY coordinate system again. Of course, we'll set the origin at the location of the object, which is the toy car. Now let's think about all the forces acting on the object, which we'll represent as a single dot. First, we have two friends pushing the car to the right, and their pushing forces are F1 and F2. Let's say the first friend pushes a bit harder, so we'll draw F1 as a slightly longer arrow. Next, we'll add the three forces we just talked about to the free body diagram. Gravity acts downward and is shown as an arrow labeled W. The normal force acts perpendicular to the surface, so in this case, that's an upward arrow labeled N. And because the car is moving to the right, the friction force acts in the opposite direction to the left. We'll label that F. So now we can clearly see that 5 different forces are acting on a single object in this situation. Now that we've drawn our free body diagram, let's figure out the net force acting on the toy car. In the vertical direction, the downward gravitational force and the upward normal force cancel each other out. That means the net force in the vertical direction is 0. Now let's look at the horizontal direction. We have three forces, F1 and F2 acting to the right, and friction acting to the left. If we add up these three as vectors, we get the total net force by adding the two rightward forces and subtracting the leftward friction. The result, as shown by the blue arrow in the diagram, is a net force to the right. So even though the situation looks complicated, by analyzing all the forces through a free body diagram, we can clearly find the net force acting on the object. Once you fully understand this process, you'll be able to solve many types of motion problems that often appear on tests. Next, let's draw a free body diagram for a motion that happens on an inclined plane. This next example is a very common one that appears in many physics problems: motion on a sloped surface. In the figure below, a skier is sliding downhill along an inclined slope. When we analyze motion like this on a tilted surface, it's very important to set up the coordinate axes to match the slope of the motion. In our minds, it's usually easier to think about horizontal and vertical directions, but from the skier's perspective, it's much more convenient to tilt the coordinate axes so that one axis is parallel to the slope. That way, the motion becomes a horizontal motion along the slope, and it becomes much easier to analyze the forces. So as shown in the figure, we'll set up our coordinate axes so that one axis is parallel to the slope and the other is perpendicular to it. Now, following the same steps we've used before, let's draw the free body diagram. Step 1. Identify all the forces acting on the object. As we discussed earlier, whenever an object is moving on a surface, there are always three main forces: gravity, normal force, and friction. In this problem, there are no additional external forces, so we'll just include those three in the free body diagram. Step 2. Set up the coordinate system. We'll define the tilted direction along the slope as the x-axis and the direction perpendicular to the slope as the y-axis. The origin is at the skier's position. Step 3. Draw each of the three forces as vectors pointing in their correct directions. This part is very important. Gravity always acts vertically downward. The normal force acts perpendicular to the slope, pushing the skier away from the surface. And friction acts opposite to the direction of motion, so up the slope. Make sure you clearly understand the directions of these three forces. Now, the next step is to find the net force acting on the object by combining all these force vectors. As we discussed before, when we add vectors in 2 dimensions, we can break each vector into its horizontal x and vertical y components, and then add or subtract them separately. In other words, horizontal and vertical components separately to find the total. In this example, gravity is the only force that's not aligned with our tilted coordinate axes. So, we'll decompose the gravitational force into 2 components, one parallel to the slope and one perpendicular to the slope. Let's take a closer look at this in the diagram below. Using trigonometric relationships in a right triangle, we can split gravity into those 2 components like this. The parallel component of gravity equals the total weight W times sin theta, and the perpendicular component equals the total weight W times cos theta. This process is what we call resolving a vector into components. Now, taking all of these forces into account, let's find the net force acting on the skier. Just like before, the 2 perpendicular forces, gravity's perpendicular component and the normal force, cancel each other out. So what's left is the difference between the 2 parallel forces, the parallel component of gravity and the uphill friction force. That difference becomes the net force acting along the slope, which is shown in the right. This type of problem appears very frequently on tests, so make sure you practice drawing these diagrams several times until you feel completely comfortable with them. Finally, let's wrap up today's lesson by reviewing the concept of a free body diagram together with Newton's third law, the law of action and reaction, using a diagram. Let's go back to a simple example, a bag resting on a table. We already discussed the free body diagram for this earlier, and it looks like this. In this case, the object is the bag sitting on the table, and there are 2 agents applying forces, the earth and the table. The earth pulls the bag downward with gravity, and the table pushes the bag upward with a normal force that's perpendicular to the surface. Since these 2 forces are equal in magnitude and opposite in direction, the net force on the bag is 0. That's a quick review of what we covered earlier. Now let's explain the same situation using Newton's third law. As we reviewed last time, the law of action and reaction describes a pair of forces between 2 objects, the agent and the object. Each force in the pair acts on a different object, but they're equal in magnitude and opposite in direction. In this case, we have one object, the bag, and 2 agents, the earth and the table. So we can draw 2 separate pairs of action-reaction diagrams. one for the bag and the earth, and the other for the bag and the table. On the left side, we have the pair that shows the interaction between the bag and the earth. In the first diagram, the bag is the object and the earth is the agent. The earth pulls the bag downward with gravity. In the reaction diagram, we switch roles, the earth becomes the object and the bag becomes the agent. So now the bag pulls the earth upward with an equal and opposite gravitational force, shown by the blue arrow pointing upward. This is a long-range force. Gravity acts between the two objects even though they aren't in contact. Does that make sense? In the same way, we can draw another pair of diagrams for the interaction between the bag and the table, just like the ones on the right side of the figure. Try drawing these on your own. It's a great way to test your understanding. So today we learned how to use free body diagrams to visually analyze the forces acting on an object. In our next lesson, we'll combine what we've learned about forces and motion, and we'll start solving different types of problems quantitatively. That's all for today's lesson. And now, you are a free body. Great work, everyone.